Good morning. I am Mr. Ish. Thank you for joining me for this video. Thank you for liking and for subscribing. In this video, we are formalizing this area, the potential confusing points in derivatives. There are four of these which we will look at, but they all relate to a single concept or aspect of derivatives, and that is related to exponents and related to bases. All right. There are four potential confusion points that arise as a result of derivatives which involve exponents and bases. And you can say there are four potential cases. We will look at each case one at a time with examples and show you how you should not confuse yourself with exactly what you are seeing. So let us look here at case number one. The case number one with regards to derivatives is to do with a setup such as you're looking at something like this, a to the power of b, and we're looking at derivative of this. Now the case over here involves here specifically a is equal to a constant, right? Like a number or a constant, and b here is also a constant. In this case, when you're looking at something like this, you might as well be looking at something such as an example like 2 to the power of 3, and here the derivative will always be a 0 because essentially you're here doing a derivative of a constant. And likewise, you could have very well be looking at something like this. You can say 2 to the power of pi, and you're doing the derivative of this, and it's still a constant. You can do a derivative of, let's say, e to the power of 3, and again it's going to be a constant. The reason why this specific case A, where you have a constant to the power of constant, is always equal to 0, because at the end all of these are all y equals horizontal lines b, where these are b values, and these are all horizontal lines, and horizontal lines have a slope which ends up being 0 because they're horizontal. Therefore the rate of change is 0 and the derivative is 0. So case A, be wary of this and don't let this confuse you into anything other than you presenting this as an answer here, and you should always be right in that case. Let's look at case B. I've presented case B here in a very formalized manner because we're trying to make this a topic, a formalized one, so that you are more aware of it. But remember, just don't let this presentation here confuse you, because much of this is intuitive and much of this you may never have thought about, and you might automatically be doing it right. We're just addressing potential areas of confusion. We are looking here at a case where now the base, which here I've represented as an f, is very well a variable, but your exponent here happens to be a constant. The only reason why we've presented here this expression in a very formalized manner is because at times this variable here can very well be a composite and not just a simple case. And let me show you two examples where you should be wary of this case, where the base is a variable and the exponent is a constant. Consider you're doing a derivative, and remember we're doing here in all cases derivative of each of these four cases. You're looking at something which looks very much like this, derivative of x cubed. You have a variable base but a constant exponent. Here you know very well it's 3x squared. It doesn't really follow this case, though it does, but you don't visually see it because we're not dealing here with a composite. Now contrast this very sharply with something which looks like 5x minus 2 to the power of 3. Now here you do the chain rule, which would then employ and bring in this via the power rule. We're using the power rule here, but here the chain rule would employ the power rule in addition to the chain components. You would do d over du, you would have u cube, and then du over dx, you'll have 5x minus 2. You'll do the derivative here, 3u squared, and then here you do the derivative, you'll have a 5. And then when you bring it all together, you have a 15. You resubstitute the u, which is 5x minus 2 to the power of 2, and that's exactly what you're seeing here. You have the derivative coming out here in terms of the 5 which attached with the 3 which came out from here. You got a 15. You still have this f to the power of b minus 1, the exponent decreased down. You still have the b component over here, which is very well married in with the derivative of the variable combined together, and this is exactly what you're seeing. So these are the two cases you should be aware of, one of this, one of this. The simple case where this form doesn't truly play out, and then the slightly more composite case where the chain rule brings in this type of an expression and that type of a result. But in this case, again, variable is a base, exponent is a constant, and you have seen stuff like this. Now the third case to be aware of is this, where specifically here the base which you're seeing is a constant, but then that constant is attached very well to an exponent which is a variable. And you know cases like this, except here we have a more formalized presentation. The very basic case over here, you know it's easy, and I'll still present you that, but this expression here deals with the composite version of that case where the chain rule comes into play. Look at it, easy cases. You're doing derivative of b to the x. You know that is b to the x times ln b. Another easy case, you're doing derivative of 2 to the x, which is 2 to the x ln 2. And you're seeing that this right here has, both cases have a constant base but a variable exponent, and everything plays out relatively as you see over here. You don't have this component coming in here because you don't have a chain rule. But let's bring in a chain rule component. We're looking at d or dx, we're looking at 3 to the power of x cubed minus 3. Now we have a chain rule which will come in because this function right here is a composite, or it is something more than just a simple case. You would have to use a chain rule. D over du, 3 to the u, and then du over dx, we have x cubed minus 3, which is why then you see the derivative of that exponent coming in, playing with everything over here. You'll do the derivative of x cubed minus 3, which is just a 3x squared. That's my derivative of f of x coming right over here. Then 3 to the u is just no different than you saying 3 to the u ln 3, and then u can be resubstituted, and then you have 3x squared times 3 to the x cube minus 3 times ln 3. And this right here very well mirrors exactly what you see right here. You have your original component, which is 3 to the power of x cube minus 3. You have your natural log component, which is right here. Then you have the derivative of your exponent, which is right over here. So don't let these more formalized presentations confuse you, because much of this is intuitive, but we're looking at the 4 separate cases for which you should not end up being confused by. Now the fourth case is the most difficult one to deal with, but it is perhaps the most easy one to see and notice. Why? Because in this case you're looking at something which looks like this, like that. You have a base which is a variable, right? And you've seen questions like these, and then you have an exponent which is also a variable. So how can you even miss that? You can't. It's very easy to recognize, but then to solve these it's difficult. When you're doing the derivative of something like this, then you have to do the implicit differentiation, and you know all of that, implicit differentiation, but you have to do the specific form of implicit differentiation, and that right there is logarithmic differentiation, and you have to be familiar with that. And I've presented a video, and we have that in my previous videos on the derivatives. I have a one on logarithmic differentiation. When you see something like this, you're thinking about logarithmic differentiation. There really is no other way to handle it other than that. And we can just present you an example over here. We have an example which looks like this. Y is equal to x root x, and you have to do the derivative of this. The implicit differentiation and the logarithmic differentiation route will develop after you have modified this by means of a natural log. Natural log y is equal to root x and natural log x. You see this? And now you do the derivative of this, or the implicit differentiation of this. And you have a product rule which would come over here. You will do d over dy, ln y dy over dx, because this right here is always what you're solving for. Do the product rule. Here's my f function, here's my g function. The g function times the derivative of the f function plus the f function times the derivative of the g function. The derivative of natural log y will be nothing more than 1 over y, which is attached to this dy over dx. Here you're getting a ln x. Derivative of root x is 1 over 2 root x. Here you have a root x. Derivative of natural log x is just 1 over x. Then dy over dx is equal to, you take 1 over y on the other side, it becomes y. And then you have ln x plus root x. You would have to do a common denominator, and you can. A good common denominator here would be 2x. 2 root x goes in 2x root x times, you'll have a root x here. X goes in 2x 2 times, you'll have that over there. And you can do this algebra on the side, right? You can do an isolation over here, and you can do the resubstitution of y. Remember, that's logarithmic differentiation. You can resubstitute y for exactly what it was, x to the power of root x. You'll isolate a root x here on the top, and then that'll bring in ln x plus 2, and then you have a 2x on the bottom. This x and that root x can cancel out, so you can make this into a root x, and you can totally eliminate this component here on the top in terms of the root x. And your question is done. We can just rewrite it here more cleanly. X root x, this right here is all your derivative dy over dx. All of that is your answer of your implicit differentiation or your logarithmic differentiation. It's this ln x plus 2 divided by 2 root x. and your answer is complete. But remember, in this case 4, we had a variable base and we had an exponent variable, and this is the most difficult case to handle in terms of the derivative, but it's the most easy case to see because you know exactly what you're seeing. So keep in mind the 4 cases: case 1, case 2, case 3, case 4. In one case you have both exponent and the base, which are constants. In one case you have an exponent which is a variable and the base is constant, and in another case those two items flip, and in the 4th case everything is a variable. And don't let these potential 4 cases be confusing for you in terms of derivatives. Much of this is intuitive, but here we have formalized that so you are more aware of this as you see it. Thank you for watching. Have a nice day.